it's Emily, and today is day 88 of the Odin Project. Today I completed my binary search trees project for the JavaScript course, so I'm going to talk through how I finished that project and what my next steps are. As a quick reference, the goal of this project is to write a factory function which produces a binary search tree, and to write methods that go along with that factory function that allow you to manipulate the binary search tree. I ended yesterday's vlog by describing the level order method that I wrote. The level order method traverses the binary search tree using a breadth first search method where you go level by level visiting each node. And if a callback function is passed into that method, then the function will pass each node into that callback function as the node is visited. If no callback function is provided, then that method will just return an array containing the values of all of the nodes that were visited. The next three methods that I wrote today follow a similar pattern to that method, where we're still traversing the binary search tree and we're still passing the nodes into a callback function if it's provided. Otherwise, we are pushing the values of the nodes that we visited into an array to return. The three methods that I wrote today all use depth first search patterns. So instead of going horizontally level by level visiting each node, we actually go down the binary search tree visiting in a different pattern. So the first pattern is called pre-order. So I wrote a method here on the right side of the screen called pre-order, which takes the root node and then can take a callback function, and it essentially visits the root node first, then it visits the left branch, and then the right branch. So for example, if we include the root node as this 8 node that you see here on the top of the binary search tree, then we would visit the 8 node first, and then we would work our way down to the left branch. But this function recursively calls each node, so this 3 then becomes the new root node. And so we would visit that as the root node first, and then we would look at the 3's left-hand side branch. And then again, we would do the same with 1, and the left-hand branch would return null, so then we visit the right-hand branch, and essentially we just recursively work our way through the entire binary search tree this way. The next method is called in order, and this one is very similar, except we visit the left side branch first, and then we visit the root node, and then we visit the right-hand branch. And again, each node is called recursively into this function, so we traverse the entire binary search tree. And the third method is called post order. And with this one, we visit the left branch first, then we visit the right branch, and then finally we visit the root node. The next method that I wrote is called height, which returns the height of a given node. Height is defined by the number of edges between that node and the leaf node. And so we basically just calculate all the paths between that node and a leaf node and return the longest path, which is that node's given height. So for example, if we pass this 8 node into that method, then we can see that one of the longest paths would be to go from 8 to 3 to 6 to 4. So if we count these edges, it would be 1, 2, 3, and that would be our height that we would return. And with this method, I did use recursive calling to essentially traverse the binary search tree until leaf node was reached. The next method that I wrote is called depth, and this returns the depth of a given node. Depth is defined by the distance of a node from the root node. So for example, if we were looking for the depth of this 6 node, then we can see that there are 1, 2 edges between the 6 node and the root node, so the depth of this node would be 2. Instead of using recursive calling for this method, I did a more iterative method where I set the node depth equal to 0, and then I traversed the binary search tree, and each time I traversed it, I added 1 to the node depth. And then as soon as I reached a node whose data matched the data that I was looking for, then I would return the node depth. Next, I wrote a method called isBalanced, which takes a root node and then we'll check to see if that entire binary search tree is balanced or not. And the definition of a balanced binary search tree is where the difference between the height of the left branch and the right branch is no greater than 1 for all of the nodes in the binary search tree. So for this one, I actually used my height method to calculate the left height and the right height for each node, and then I would compare them. And if the difference between them was ever greater than 1, then the function would return false. Otherwise, if we recurse through the entire binary search tree and none of the differences in heights is greater than 1, then we return true. And finally, I wrote a method called rebalance, which accepts a root node and then will rebalance it, so it creates a balanced binary search tree. This one was pretty easy. You essentially just create an array out of the unbalanced binary search tree, and then you can pass that array into your binary search tree factory function, thereby redefining your binary search tree, which is now balanced. The last step of this project is to write a simple driver script, which essentially tests all of these methods to make sure that they are working. So I console.logged all of the steps for the script, and then I wrote the associated functions for testing the methods and printed the results to the console. So you'll see here, first we create an array of random numbers, we print the binary search tree, we confirm that it's balanced using our isBalanced method, and then we print all of the elements in the various orders that we reviewed, so level, pre, post, and in order. Then we intentionally unbalance the tree by inserting nodes that are greater than 100. So you can see here we have a heavy-sided right branch. And then we confirm that the tree is unbalanced by again calling isBalanced method. And then we use our rebalance method to rebalance the binary search tree. We confirm that it's balanced, and then we print out all of our elements in the various orders. That is everything that we had to do for this project. Tomorrow morning I am going to take some time to do another review of my code because I did finish it just right at the end of the day today, and I'm also going to do some more error handling. After I complete all of that, my next step is to start the Knight's Travails project. That is all that I have for today, so thank you so much for tuning in. If you like these updates, be sure to hit the like button and subscribe if you'd like to continue following along on our web dev journey. But I hope that you have a great day, and I will see you next time.